Pluto, a distant and enigmatic celestial body, was once considered a part of our solar system's planetary assembly. However, recent statements from prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited interest in Pluto with their surprising claims about its potential interaction with Neptune. This raises intriguing questions. How could such an event occur, and what might the consequences be? Are we witnessing a fascinating cosmic phenomenon, or is there something else at play? Join us as we explore the possible outcomes of a Pluto-Neptune collision. Once categorized as a planet, Pluto was reclassified as a dwarf planet largely due to its unusual orbit, which has continued to captivate astronomers. According to recent analyses from leading scientists, Pluto's orbit comes dangerously close to Neptune's, prompting Tyson and Kaku to warn of a potential catastrophic collision that could pose a serious threat to Earth. But how is such an event even feasible? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an astounding 248 years to complete a single revolution. Since its discovery in 1930, Pluto has not finished one complete orbit. Its path is characterized by an extremely elliptical shape, deviating significantly from the nearly circular orbits of the major planets. Furthermore, Pluto's orbit is tilted at an angle of 17 degrees to the ecliptic plane, making its trajectory particularly erratic compared to those of other planets. This eccentricity adds complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune does, challenging our expectations based on their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery, as astronomers sought to understand its peculiar path compared to the more regular orbits of other planets, which are relatively close to the ecliptic plane. Pluto's orbit stands out due to its steep inclination and elongated shape. The mystery deepens with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amidst these complexities illustrates the intricate mechanics of celestial dynamics. The three-body problem in astronomy involves determining how three bodies like Pluto, Neptune, and the Sun interact and affect each other's movements through gravity. It's akin to predicting where these celestial bodies will be based on their starting positions and the gravitational forces they exert on one another. In Pluto's case, this problem highlights how the orbits of Neptune and the Sun interact with Pluto's trajectory. Terms such as libration and precession are crucial in understanding this dynamic. In the context of Pluto and Neptune, libration indicates that whenever Pluto crosses Neptune's orbit, it is positioned approximately 90 degrees away from Neptune. This spatial separation is vital in preventing their orbits from colliding. Conversely, precession refers to the vertical movement of a celestial body in its orbit, meaning that when Pluto approaches Neptune or another giant planet, it is situated above the orbital plane, providing an additional safeguard against potential collisions. Another essential factor in this equation is the VZK precession, named after the researchers von Zeipel, Kappas, and L.V., who studied how objects move in space. This phenomenon describes how three celestial bodies like Pluto, Neptune, and the Sun influence each other's movements through gravitational attraction. Understanding the VZK precession helps clarify why Pluto's orbit is so unusual. Despite its seemingly chaotic path, Pluto's orbit remains stable over long periods, on the order of billions of years. This stability suggests that Pluto's journey around the Sun, while erratic in appearance, follows an underlying order. Predicting future events, especially those involving erratic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While mathematical simulations provide valuable insights into the future trajectories of celestial bodies, they also emphasize the limitations of our understanding of these complex gravitational interactions. Tyson's viewpoint on Pluto's renaming and Kaku's emphasis on the chaotic nature of celestial mechanics both underscore the necessity for continuous exploration and a flexible understanding of our universe. The potential collision scenario illustrates the dynamic and complex interactions within our solar system, ultimately reminding us of the vast yet still unclear areas in our comprehension of space. Through persistent research and observation, we strive to unravel these mysteries, ensuring that our knowledge evolves alongside the ever-expanding universe.